Hello again. So this is just a quick video to introduce representing fixed point iteration on a graph. This is still the bit of the specification we're looking at. We're going to also talk a bit about, or see today, how fixed point iteration can sometimes fail and showing that graphically, but we'll talk more about that in a later lesson. Right. On Desmos, you can look at a graph nice and easily, and I've made this page, which I'll send you a link to so you can use it. You can change this to be the equation or the function that you're looking at, the equation you're trying to solve. And you can change this bit to be the rearrangement you've got of it so that you can do this with all the questions you're doing and get a feel for it by playing around with it. But anyway, the example we looked at the end of last time was this quintic with three roots, making up their solution of those three numbers. And one of the rearrangements that we saw last time, this one, found a couple of the roots with different starting points. So let's have a look at that. That's the graph of y equals g of x. Remember we rearranged this equals 0, f of x equals 0 to be g of x equals x. So if we draw the graph of y equals g of x and the graph of y equals x, those two are going to cross at the same places that this is 0. So best example here is that one. The black graph crosses the x-axis. That's the x-coordinate we want. It's also the x-coordinate of where the blue and the green cross. Similarly, over here, there's a root of the original equation there, and directly above that, just to the left of these dots, directly there, that one is the intersection of the green and blue. And there's another one over here where the black graph intersects with the x-axis, and directly below that, this one is where the blue and green cross. G of x is equal to x there as well. So the values of x that make f of x equal 0 are the same ones that make g of x equal x. And that's the point. I'm going to get rid of f of x because we kind of turned our problem into where do these two graphs meet. And that's what we do. We plug x repeatedly into this formula and it gives us new ones out. And showing that process on the graph is kind of nice and pretty. So say that's my starting point. X equals 0.7. I draw a line up to g of x. The y coordinate of that point is now going to be my next x, isn't it? My x1. This is x0. This is going to be x1. So if I pop from there across to y equals x, I'll be above the correct x coordinate now for x1. So that's what I'll do. I'll draw that line across to y equals x. So now I'm at the x coordinate x1. I'm not going to go back down to the x-axis though. From there, after the first one, I always just go back to g of x, up or down, and then across to y equals x. So we'll look at that with the second iteration. Slide that along to it. So we're going up to y equals x, up to g of x, and then along to y equals x. And we just keep repeating that process. So that's our new x number, that's x2. And then we plug that into g of x, and then we go across to y equals x to get the new x value, x3. Okay, so I just keep sliding the slider along and it will keep doing that on the graph for me. This is what we call a staircase diagram. For obvious reasons, it looks like a staircase. And if I change my starting point, it might behave differently. Anywhere near that root, it zooms in on that root with a staircase. Okay. If I come over here to try and find this root, nothing doing. It just moves away from it and finds one of the other two. So there, it's zooming off with a staircase to find that root between -1 and -5. And we saw this yesterday. This rearrangement doesn't find that middle root. The reason for that is the steepness of g of x there is too steep. It's steeper than y equals x. And that's a key thing that we need to know, and we'll talk about why and what that means later. So that's staircase diagrams. In this example, you're going to get a cobweb. So the black graph is y equals f of x. So we want to find the x-coordinate of that point there. Directly above it is where g of x crosses y equals x. I'm going to get rid of f of x for clarity. And so, I mean, let's start at 0 in this one. And if I just start doing my iterations, I go up to the graph of g of x and then across to y equals x. So I've found an example of where it breaks, and I get stuck in a loop. So here, I'm just going to get 0, 1, 0, 1, 0, 1 coming out. So that's not great. We call that oscillating between two values. But if I just move up to a starting point of 0.2, then you can see it cobwebs in and hits the graph. Okay, we'll talk again later about why it's a cobweb versus a staircase, but essentially it's just because this gradient here is negative, and on the staircase questions it's positive. The important thing though is that it's shallow. If this had been steeper than a gradient of -1, so steeply downhill, it wouldn't have converged on that point, it would have diverged away from it. So just to recap then, because you're going to get to practice this a bit later, when you're drawing these diagrams, you go from your original value up to the graph of your rearrangement g of x, and then you go along to y equals x. And then after that, you constantly just go back and forth, up and down, up or down to g of x, and then across to y equals x. It's hard to go wrong with that because you'll have just done across when you need to go up or down, and you've just done up or down when you need to go across. As I said in the work, there's a link to that Desmos graph, and you can play around with it, and that should help you to draw your own graphs. Good luck.